Today we're going to talk about how to handle initial rate data questions when the data is not consistent for two different trials for one of the chemicals. When I first start analyzing these types of questions, I look for data that remains the same so that I can just focus on the other chemical. Right away, my eyes are drawn to this area where the hypochlorite ion starts at 0.18. Or I could use the data where it remains at 0.09. I'm going to choose to go with the first chunk of data and compare experiments 1 and 2 to figure out the order for the iodide ion. Okay, so firstly, I see that we have a 0.12 molarity and a 0.06 molarity. Right away, my eyes see that this is a 2-to-1 ratio. Now I'm going to compare that with the initial rate on that part of the data table. This is a little bit more difficult to see, so if you can't see the ratio right here, I would put these numbers into your calculator to find the ratio between these numbers. And when I plug that in, I find out that this ratio is 2-to-1. So really what I'm comparing is I'm trying to see if this change in reactants concentration affects the rate. And it looks like that these are directly proportional. The x in this case is going to be equal to 1. Now, I visualize my rate law forming a little bit in my mind, and I know that that rate's going to be equal to a k, and that the iodide concentration will be first order. Now we have to figure out the hypochlorite ion. That one's a little bit more interesting. If you look closely at the data, none of these data are the same number. There's no time when the iodide ion is held constant. So what we do is we set up our equation a little bit differently. I'm going to take the second two pieces of data, experiments 2 and 3, and compare those. I already know that my 0.06 and 0.03 is a 2-to-1 ratio, and I know for iodide that is a first order relationship. Now I'm going to take that piece and I'm going to multiply it times my more interesting information, the thing that we are looking for now. This is where our hypochlorite ion also doubles. You see the 0.09 to the 0.18. That is a 2-to-1 relationship. And I don't know if that data is affected by a particular exponent or not yet. Now we'll check and we'll put in these initial rate data, the 3.95 times 10 to the negative 2. Please notice how I'm not doing this part in my head. It's very important to be careful with the times 10 to the stuff parts of the numbers. We do have a times 10 to the negative 2 and a times 10 to the negative 3. Try not to do the math in your head when you have those kinds of exponents. So I'll check this in my calculator and I'll see that the relationship between these numbers is actually 4-to-1. Now part of that change is caused by our iodide ion concentration changing. So we can actually simplify our math by multiplying both sides by 1/2, which simplifies our ratios. Now this is looking a little messy, so I'm going to simplify it down on the bottom. We have our 2-to-1 ratio from our hypochlorite ion and our 2-to-1 ratio left over for our initial rate data. Now we can see that the hypochlorite ion is directly proportional to the initial rate change, so we can see that y equals 1, and now we can modify our rate law to include a first order hypochlorite ion, which is how you find the rate law for a set of data that does not have a consistent chemical. Now that we know the rate law, answering the remaining questions is a piece of cake. Now we just have to find the value of the rate constant. To do that, you can pick any line of data. I like to choose the first line of data so that I don't get confused with my numbers and my eyes don't jump around. So let's put it in, 7.91 times 10 to the negative 2, and that's with units molarity per second equals a mystery K times 0.12 molarity times 0.18 molarity. When we simplify this, we'll find that our K is equal to 3.7 when you round properly, with units of 1 over molarity times seconds. The next portion of the question says to calculate the initial rate when both I negative and OCl negative are initially present at 0.15 molarity. Okay, so all we have to do is plug and chug. The rate will be equal to our rate constant, 3.7 times 0.15 molarity times 0.15 molarity. Now I've carried all my numbers in my calculator, so my answer might be a little bit different than yours, but I calculated the rate to be 8.2 times 10 to the negative 2 molarity per second. I hope that was helpful.